Okay, does it work? All right, let's start. So last time we were talking about Shiger inequality, which basically says that if you want to check if a graph is an expander, it's just enough to check if the second eigenvalue of normalized Laplacian is big or not, right? And we have proved one side of the inequality, which means that if there is a sparse cut, then the second eigenvalue must be small. Now, we didn't finish the second part, which says that if the second eigenvalue is small, then you can find a sparse cut. Okay, and just to recall, the statement that we want to show is that, well, given any vector x such that it is orthogonal to a degree vector d, then you can find a cut S such that the conductance is at most this thing. And we know that there is an X such that this ratio is at most lambda 2 of the normalized Laplacian. And that's why it's enough to prove this theorem. Okay? And there were several steps. But the way to think about it is that when you are given an x, you think of x as basically an embedding of a node into real lines. So you have x u1, x u2, and this is and so on in real line. Okay, and what we would do is that we will like kind of massage x a bit, so that it's easy to extract a sparse cut from this vector. And what we did is that, by the way, as a spoiler, the way to extract the cut actually will be like this. Before I recall this proof again. It's really just you look at this x vector and sort the vertices according to this x vector, right? So you have the order of vertices here. And then you really just look at like a sweep cut again. So looking at a cut such that it's like the first I nodes in this order. One of them will be good for you. That will be the algorithm actually. But to prove that, we need some massaging to this x so that you can prove that. And what did we do? The first step is to say that we make it center. How? Well, you literally just translate x a bit, and after some translation, like you set y to be the vector x minus some scalar and one vector, such that y has the property that if this is 0, then all the nodes on the negative side is small. That is, all of these nodes. Let's call it like maybe v less than 0 and v more than 0. All of this, both of this set. What do we have here? Do you remember?
V less than 0 less than v of total v.
Yeah, it's like less than half. And on the other side, you have that too. So that's what we do for y, and we prove that just by doing this translation, the ratio here is always getting better, like it's smaller. And then for z, we just say that okay, both of these are small, and we just say that, okay, if we define z to be a vector that contains one of the two, then like one of them will be better. So define z to be, c is either y minus or y plus, where y minus is this thing, and y plus is this thing. One of them will be such that the ratio is not increasing. Okay. So what we have until now is basically the vector y such that it's non-negative. So, and if you sum up all the degree of non-negative entry of y, is on the smaller side. It's not more than half. Okay. So now, so maybe just write it down. So this is z, and it's now non-negative. This is 0, and this is some like cu. A bunch of things, a bunch of nodes is here, but there are some node which is non-zero, and so on. Okay. And this, the degree of all non-zero guy is less than, total degree of non-zero guy is less than half. Okay. All right. So now I'm gonna show now that, okay, if you do if you define, if you have this vector z, then there will be some threshold tau, such that if you look at a set more than the threshold, then this set will be a sparse cut. All right. Just to be clear, what does it mean here? If you have y, a vector y, where like this is 0, suppose that c is actually here, then this cut will correspond to this cut, right? Like, because you kind of flip the sign. Yeah. But if z is y plus, then the cut s tau here is basically this. Yeah. Right. So we just said that the x is a tau, such that this cut now, if you look back into the graph, you will have like that the conductance is small. And if we can prove this, we are done. You agree, right? Okay. So the first step to proceed is just, first I will just assume that the maximum guy in the vector z is at most 1, because I can scale z. It doesn't change the ratio here at all. Okay. So now see, like we have that the most negative one is 0, and the maximum guy is 1. Yeah. So all of the entry in z is between 0 and 1. Okay. And now how do we show that one of the sweep cut, one of the threshold cut here would be good? So we will prove this using a probabilistic argument, and we will choose tau in the random way, in this way. So the threshold tau you imagine that you sample in such a way that tau square is uniform. Is uniformly distributed in the interval 0, 1. Okay. So what does it mean? It means that if you look at the probability that tau square is less than some number, the probability that tau square is less than that number is exactly that number. So that's what I mean. Yeah. So, okay. And which means what? Which means that if you ask if tau is, what is the probability that tau is less than alpha? That's going to be alpha square. Okay. That's the distribution that we look at. And actually you can, there is an explicit density function, which is something like this. It's simple, but we don't care. We don't just, this is just for like existential argument. Yeah. Okay, now let's say now that, okay, we have the interval 0, 1, and now you choose tau is here, and define S tau to be to contain all of the node U such that ZU is more than tau. Okay, so S tau is this guy. And now the key claim is this. So what is the conductance of S tau? Is it simply the size of the cut, right? Over the volume. Now what we will do is that we will compute the expectation of the numerator and denominator. So we will just separately compute the expectation on the thing above and below. And we will see that it will be what we want. It will bound by something that we want. And although it is not the case that the fraction, how to say it, this is not the case. Expectation of fraction is not a fraction of expectation. This is not the same thing. But what do we know from here? We still know that if you have this ratio, it means that there exists a tau such that the ratio here is smaller than the fraction of the expectation. Again, we use this repeatedly, like mean of AI or BI is less than some AI, some BI. It's just, this is just this inequality. Okay. So I'm gonna say, we will prove this soon, but I'm gonna say that if we can prove this thing, the blue thing, then we are done, right? And yeah, you see that, because if the blue thing is true, then there exists tau such that this ratio is small. But this ratio is simply the conductance of S tau. So we are done. So now let's prove the blue thing. Okay. That's the really last step. So let me first prove, look at the denominator. This is both are not hard to analyze actually. So let's look at the expectation of denominator, the expectation of the volume of the set, right? Well, you really just expand the definition and see that this is the sum of the degree of all the node U, and you just ask if the node is in the set or not. The probability that the node in the set multiplied by the degree. But what is this? This happen if and only if U is, so if U is, if CU is more than tau, right? If this is tau, U will be in the set S tau if tau is less than CU. Yeah. But we know what is this thing. This is like CU square. This is the reason we choose tau to be such that tau square is uniformly distributed, because we want, at the end, we want to relate that to something square, right? So that's how we have this. And what is this thing? It's exactly Z times D times Z. All right? Okay. How about, so we have what? We have that, this thing, that here, this part is equal to CD. And now we need to analyze the thing above here. Okay. Which is, the thing above is just the size, the expectation of the size of the cut. So, well, we just use, so the expectation here equals to like you sum over all h, uv, and you ask if an h, like times the probability that an h is cut. And when is it cut? It's cut only when like one endpoint is less than tau and another endpoint is more than tau. So CV is, CV is here, CU is here. Yeah. Then that's when it is cut. And again, what is the probability that this happen? Well, it's happen only if tau is between this interval, right? And what is that? That is just like CV square minus CU square. Because the probability that tau is here is CV square, but you need to minus the probability that tau is here, which is CU square. Right. Now, once we have this, we need to do some math. So you just rewrite things, and you use Cauchy-Schwarz. Should I recall Cauchy-Schwarz? So it's really like A times B is less than the norm of A square and the norm of B square. Right? And what do you think of A and B here? Is so like,
There won't be norm squares, right?
yeah, thanks. Yeah. Good. So what would be kind of A here? It's gonna be like square root of W here. Like think of AUV is, yeah. And BUV is square root of, right? And then you apply Cauchy-Schwarz and you get this thing. But you see that this term is just exactly Z, LZ. And the second term, we can also prove that it is like, it's gonna be less than this one. So why is that? Well, so this term, is it clear? The first term is fine, right? So what is left is just to prove that this term is less than this one. And to do that, well, it's gonna be not too hard to. That is, we can see that we just use the fact. So this inequality is actually useful. That is, a plus b squared is less than 2 right? Because yeah, you can verify this. Yeah. Because like if you move things around, then you if you like subtract this from here, then you get that this is yeah. Okay, so I just apply this inequality here. But now it's kind of easy to see also that this is the same thing as summing over all nodes u instead of summing over all h. But how much, like how many times that you count the zu square? It's just like it's just the same thing as like summing over like degree, like summing over all edges incident to u times 2. So that's why you have degree, 2 times degree here. But degree is, I just write degree as d here. So that is just, this term here is just 2z dz. Okay. So we have what? We have, here we have a square root of c times c dz. So this thing cancel, and you get this, which is what we want. Okay, that's the proof. So the point is, like, this is just the proof, but you see, all of this is just a proof that there exists a sweep cut, which is good. There is, like, once you have the vector x, given the vector x, here there exists some sweep cut, either from the left or from the right. Doesn't matter, it's the same thing because you flip it. There exists a sweep cut such that the conductance of that sweep cut, one of them, will be as small as this. Yeah. And to do that, we just move it to be center and choose one of the good side, and then try to prove something. Yeah. Okay. So just from the proof here, you can see that I kind of already said it, but it really gives you an algorithm, right? So suppose that you have a graph and you want to find a sparse cut S. By sparse, I mean that the conductance is small. How small? Like square root of lambda, which means that it is less than square root of the conductance. How to do that? Well, we just really start by computing a second eigenvector of the normalized Laplacian. And then we just multiply, like scale it by some degree factor, scale this second eigenvector to get x. And now x is such that it's orthogonal to D, and this ratio is second eigenvalue. And now from the proof that we just saw, you can see that we literally just sort a node by x, and define like a sweep cut for each I. You get a prefix cut, and just return the best one. That's the algorithm. And yeah, so it is correct as we kind of discussed above. And you see, like, can someone tell me that instead of V2, the second eigen vector, if we are just given some vector V, such that this ratio is quite small. Y is fine. Why is it good too? Like, why would we get this cut with this conductance, maybe with plus epsilon? Why is it okay? Well, this is because you see, when we where is it? When we try to prove the second direction of Shiger inequality, we actually say that, well, given any x, we will get a cut such. Given any x here, we will get a cut such that the ratio, like the conductance, is small with respect to this ratio of x. It doesn't matter if x is really corresponding to second eigenvector, right? Any vector x that give a good ratio, the algorithm will find a cut which is good. We just know by the math that if x corresponds to a second eigenvector, it's going to be good, but any good vector is fine. Yeah. So you see that given any vector v such that this ratio is small, if we just multiply, like compute x to be like what we do here, x is this times v, then you will get that basically you will get that x here will be orthogonal to D, and this ratio is going to be this plus epsilon. And just apply the same thing, and you get that the cut is going to be like, the cut going to have small conductance with some slack epsilon here.
Each function has the coefficient square root of 2.
Say it again.
Epsilon should have a coefficient.
Oh yeah. Thanks. Yeah. Okay. All right, and you can see that all of the algorithmic step here are super easy once you have some vector that you want. Like, you really just sort things and you sweep through the, like, you have an order of vertices and you find a sparse cut with respect to this order. So the sorting is n log n, and finding a cut with smallest conductance in all this like sweep cut, all this nested cut, is gonna take linear time too. So everything is fast except computing eigenvector. Okay. And by the way, this is just one possible project. Just want to mention it here. That is, there is some like other paper that actually might be able to give alternative analysis and algorithm to find this sparse cut based on eigenvector. The analysis is based on something called median cut, which might be more intuitive. And also, the algorithm might be better because instead of looking at n many cuts here and query for like which all of these n cut, which one is the sparsest one. It should use like less, like just query just log n many cuts instead of n many cuts. So I think it like the analysis from the section 7 of this paper might give something like this. It works for PageRank, but I think it should work for Shiger cut too. But I think it's maybe a good thing to try as a possible small project. And by the way, Shiger inequality, there are like several extensions of it. Here we describe the version where it is for undirected graph and for this conductance cut and small conductance cut. There are some work on directed graph too, and you see Shiger inequalities kind of say that if lambda 2 is big, then the graph is an expander. If lambda 2 is small, then there exists a sparse cut. What can we say about lambda k? Well, we can actually say something like, if lambda k is, first of all, if lambda k is really 0, then we saw that there must exist k different connected component. But if lambda k is close to 0, we can actually like prove as well that the graph is kind of close to like kind of have k cluster. So that is a cool thing. Like just by looking at the lambda k, you kind of know whether the graph have k cluster or not. So like it's a good for graph clustering. People use it actually. Yeah. And I want to mention, okay. One thing is that we need some scribe for the next file. Is there anyone who didn't scribe yet? Do you want to try?
Which one are these?
This one. Yeah. Okay. Thanks. Okay. So we saw something about lambda 2, and I mentioned briefly about lambda k. What? Actually, there is some like interpretation of lambda n too. The last one, the biggest one. So basically, when lambda 2 corresponds to sparsest cut, it turns out that lambda n corresponds to maximum cut. And we actually, I will tell you the proof in the extreme case. That is, first of all, I'm gonna show that lambda n of normalized Laplacian is always at most 2, which means that all of the eigenvalue is between 0 and 1. We saw last time that the eigenvalue, like the smallest one is 0. And now the biggest one is at most 2. And now, if it turns out that lambda n achieved its maximum is 2, then the graph is the graph at least has a component which is bipartite. And if it is connected, then the graph is bipartite. Which means, so suppose that the graph is connected and bipartite. It means what? It means that you have 2 components, and there exists like a cut, the maximum possible cut that cut every edges. Yeah. It will be the case actually that if lambda n is close to 2, then the graph is close to being bipartite. So like there might be some few number of edges here, but you can find like you can cut almost all edges still. but we will just prove the extreme case here. Okay. So first, just by the variation characterization of eigenvalue, recall that lambda n is just the maximum is the maximum ratio of the Rayleigh quotient, yeah, and which is you can rewrite it as this thing. And now we see that like how to prove that lambda n is at most 2. Well, I will prove that this thing is at most 0, at least 0. So do I no yeah right, yeah, because suppose that we have that maybe just go through this. What like to prove this, I will prove that this thing is at least 0. And let's look at this first maybe. 2 minus lambda n is just this thing. And I want to put max out of this, so I get min. Like it's minus max, you get min here instead. Right? And the numerator, you have this term. But you can see that the numerator here, this is just, well, by doing the math, you have this thing minus this thing, which is this. Yeah. So this is and this is like a square, so it's non-negative. So you're done. So lambda n is 2 minus lambda n is at least 0. So lambda n is at most 2. Okay. And let's do this quickly. Well, why is it the case that lambda n is 2 if and only if there exists a connected component which is bipartite? So suppose that there is a bipartite component, right? So let's say that there is bipartite component LR and maybe some other component. So this part is bipartite. There are some other connected component. Well, let's look at the vector x such that I assign xu to be everything here to be 0, except that this you get minus 1, this part you get 1. And just look at this thing. So know that this, well, is here, right? So this thing is 2 minus lambda n, and this is 2 minus lambda n. So this thing, when you plug this x in, you will get 0, because everything here is 0 anyway, and on the component which is bipartite, they like whenever you have an edge, one gonna be 1 and another one is minus 1, so you cancel out perfectly, so you get 0. Yeah. And so lambda n is 0, is 2, when there exists a bipartite component. And another direction is kind of similar, which I think I will just skip. You can just read the notes. Yeah. The point is just lambda n is kind of measure how close you are to bipartite graph. And if it's big, then you have cut that almost cut everything. If the graph is connected, yeah. If the graph is connected and bipartite and close to bipartite, there exists a cut that almost cut all of the edges. I will talk about the power method. This is the main thing I want to talk about.
Sorry, just to clarify, if it's bipartite, then the mid cut would be the max cut. So you have like lambda 2 is equal to lambda n. Is that what's yours?
No. So
What's the definition of max cut?
max cut is a cut such that it's just max cut is. Sorry, I will come back to you. Okay. Max cut is just a set of nodes such that the number of edges going out of it is maximized.
So it's not divided by the volume or something?
No. Yeah.
So that's why you cannot directly get the actual max cut from just computing the
There will be like really analogous proof of Cheeger inequality for lambda n, which is like this. And when the lambda n is close to 2, then like you can, there will be some sweep cut algorithm actually, such that it will give you a cut that cut almost all of the edges. Yeah, but I just skip it. I just talk mainly about lambda 2 because lambda 2 has something to do with expander, which is the main thing here. It's just interesting that lambda n is kind of the opposite of lambda 2. Jimmy, can you ask again? Yeah.
Maybe I think I asked a dumb question, but I'll just ask again. If it's bipartite, is lambda 2 equal to lambda n?
Not clear. No. So because lambda 2 is just about like if it is small, there exists a sparse cut.
Oh, never mind. Yeah.
Right.
Okay.
Yeah. If lambda n is large, is close to bipartite, there are like two different things. Okay. So recall that, like, okay, next topic, power method. This is gonna be important. Like, it's gonna be fast algorithm and very simple one. Nice to know. Okay, so recall that in the proof of trying to get a Cheeger cut, the sparse cut from Cheeger inequality, the only slow step is to get the second eigenvector. Right? Now we're gonna see how to get something like an approximate one, but fast. So by approximate one, I mean it's just the one such that it's still like it's orthogonal to this degree vector, but the ratio here is like close to lambda 2. Okay. We want this one. But before going to tell you how to get this, let's look at like a simpler problem, actually. That is, like you will see that it will be related at the end. But suppose now you get some positive semi-definite matrix M. So by PSD here is just positive semi-definite, which is nothing but saying that all of the is a real symmetric and all of the eigenvalue is at least 0. Okay. So you have some matrix M, and suppose that I want to estimate the largest eigenvalue and its corresponding vector. How to do that? Well, there is a super simple algorithm to do that. And the algorithm is just, you choose a random vector, x. Each coordinate is 1 or minus 1 randomly. Then you compute x times m to the k. Think of k as like log n over epsilon. So how to compute this fast? Like if you compute m to the k first, that's gonna be not so fast, right? Matrix multiplication is bad. But what you compute is like you multiply vectors to m, like, and then multiply it here and here and so on. So each of these matrix vector multiplication, it just takes you like n times the non-zero entry of the matrix. And you apply this k time. So that is just very simple algorithm, very fast. And now let's just analyze it. So now let me just rewrite things a bit by saying that lambda 1 is the biggest one now. Okay, lambda 1 is the biggest eigenvalue of m. And everything is at least 0 is PSD, right? Okay. I'm gonna prove that with quite good probability, like some constant probability. Your vector y, the algorithm power here, will return a vector y such that this ratio, which the Larry quotient here, is kind of close to lambda 1 with multiplicative factor, actually. And this is just something that is small when k is big enough. Like if k is log n over epsilon, then you can see that there's gonna be something like like if k is like big to like something like this, there's gonna be something like here. And you will get basically, it doesn't matter. Like you get like just 1 minus O of epsilon instead. So this is what we are gonna prove. Okay. But before that, can someone tell me very quickly, if you want to get better probability, what can we do? Like if we want some y such that y satisfy this with high probability, yeah, amplification, just try several y and take the best one. If you try log n many of them, then you get it with high probability. Okay, so now let's analyze the algorithm. So this is like one of the best algorithms that I like. Like it's so simple that and it works. Yeah. Okay, so let's write eigenvector of m. Okay, and you write the eigen decomposition of m, and you can see that when you look at m to the k, it's just the same thing, the same decomposition, but you multiply lambda, like you power lambda to the k, each of lambda I to the k. Okay, this is just like a linear algebra, but you can really like convince yourself because each of different eigenvector are orthogonal, so when you multiply them, everything cancels out except this term. So you get this. Okay. And now let's look at our vector x, the random guy. Like think of x as like it's just a random point in hypercube, right? You have minus 1, 1, like in the hypercube, you choose a random guy. That's x. And just write x in terms of eigenvector, vi. Okay. And so we can see that an AI here is just like, it's just how much you go in direction vi. Yeah. Okay. So so now we can just write y is just m to the k times x.
Sorry, Dr. Kwai. I was thinking about the stupid bipartite thing again.
Yeah.
Something really bothers me about it. Like,
Sure.
so if you have a bipartite graph, say like you have the same number of vertices on each partition, right? Don't you actually have like lambda 2 is 0? Because you can pick like one side is plus 1, one side is minus 1. And that's like violating like this G-group equality, right?
So, well, this kind of plus thing is only when you look at lambda.
No, I was looking at G-group equality.
Okay.
Maybe I'm just being stupid, but
I mean, first of all, like this thing is sum here and x minus this thing. It's not plus. Yeah.
right.
Okay. Yeah.
Oh, never mind. Yeah. Okay.
Yeah.
Never mind. I just.
Don't worry. Okay. Come back to here. You have a vector x, and you compute y to be just m to the k times x. So that is just this vector. Okay. All right. So now let's try to analyze it a bit. Suppose for intuition, suppose this will not be true, but suppose that lambda, the first guy is big, is 1. The first eigenvalue is big, it's just 1. And the rest is, the smaller guy are all significantly smaller, less than half, right? What should you expect? So maybe it's good to maybe just look at here. What will y look like? So y is we just wrote it here, right? Okay, but if lambda 1 is 1, then the first term is just this, and the rest of the term is here. And but if each of the lambda I, which is not for I is not 1, is less than half, then when you power it by k, then it's gonna be very small. It shrink. Basically, if you look at let's say this is an ellipsoid, okay? So this is an ellipsoid, and let's say that, okay, when you choose a random x, maybe it's in this direction. Yeah. But when you multiply x by m many times, every other direction which is not the biggest one kind of shrink very quickly. So because we assume that the ellipsoid on every direction is small, except the largest one. So when you multiply x by this ellipsoid, when you apply this linear operation to x many times, every direction is like shrinking very quickly, and then you are left with the thing that that is on the biggest direction. Okay. So basically, everything here, when you multiply it, like apply it k times, then it kind of vanish. And if AI here is not too small, if the size of AI here is not too small, sorry. Then basically y will be close to the first eigenvector. Does this intuition make sense to you? Okay. And if y is close to the first eigenvector, then you're gonna get like the ratio to be close to like the first eigenvalue. Well, now let's be formal. Like, what is the thing that we didn't make it very formal? So first thing is that we didn't argue why A1 should be not too small. And the second thing is that it might not be the case that there is a large gap. There might not be the large gap between the first eigenvalue and the rest of them. It can be the case that the second one is very close to the first one. Okay. So for the first issue, this is quite natural to expect actually, and I will prove this maybe in the exercise session. But the point is that like it's just that imagine that you have like a random vector v, any vector v, right? And if I choose a point in like a random point in hypercube, it has no bias in direction, right? Like you have like the direction is not non-biased. So with kind of not too bad probability, it's gonna be on the kind of same direction of vector v. And because of that, so the size of the inner product between x and b is gonna be not too small. Like, and if that is the case, so I claim that if you have any vector v, and I choose x randomly, the inner product between x and v is gonna be not too small, with some constant probability. And if this is the case, then you have that A1 is not gonna be too small, right? X gonna be kind of in the same, gonna be on the same direction as the first eigenvector with constant probability. Okay, let's assume this. I will prove it tomorrow, maybe. And how about the second issue? It seems more serious because the first eigenvector and the first and second eigenvalue might be very close to each other. But the point is that we don't actually need that. At the end, we don't need that the vector that we get at the end need to be close to the first eigenvector. As long as it is close to some eigenvector such that its eigenvalue is big, that is good enough for us. So what we do is we just define L to be such that let's divide the eigenvalue into two groups. L is such that all eigenvalue from lambda 1 to lambda L is a big guy. This is a big group. And the rest is less than 1 minus epsilon lambda 1. So as long as kind of our vector y is in the span of the eigenvector, the first L eigenvector, that's gonna be kind of good for us actually. All right. So now.
What we want is the first eigenvector, right?
So what we want at the end is not the first eigenvector. We just want some eigenvector such that this ratio is as big as the first eigenvalue. Yeah. So as long as it's kind of, if there are L guys of them that are big, then if it is close to any vector in this span, then it's good, basically. All right. So now, so we can just analyze it, actually. Well, what we're gonna do is I just gonna say that this ratio is close to this. Okay. So how I'm gonna do that? So let's just write it. So y times y is exactly this thing, because y can be written this way, and ym's y is this. Like you have plus 1 here. Okay. All right. And I'm gonna say that this guy is big and this guy is not too big. Big and not big. So this should be bigger than this one by like this factor. Okay. So how to do that? Well, ym is at least is just this thing. I really just truncate, like I just take the first L term in the sum here. I just take the first L term. But each of the lambda I for I less than L is bigger than this much. So I just take one factor here out to the front and I get this. And here I get this thing. Okay. So what I'm going to show is that y times y here is basically smaller than this thing. Okay. So first of all, when I write y times y, we have the first L term. This is exactly this thing. We just need to show that this term, the second term here, is also as small as this. Yeah. But now, maybe it's not good to go into the calculation, but the point is just that each of these lambda I, which is where I is more than L, they are the small guy. When you take the power of them like many times, it will shrink quickly, right? And that's why when you do that, this term gonna be small. Now, like, this will take some calculation, which I'm not sure that is good, but you can just check, right? Yeah. So this at the end is gonna be, this term at the end is gonna be something like you have this term, which is like a 1 minus epsilon to the 2k. This is like a shrinking factor that you get because they are a smaller group, the small group. And I can do some algebra and I can write this thing here. And this thing is just where this thing is this term, which is this term. Yeah. But because this term kind of shrink very quickly, it's gonna be like, basically this is gonna be small. Yeah. So you will get that like y is gonna be basically this term times some factor which is small, like close to 1. Like you have this term, the 1 here is just from, the 1 here is from here, and this term here is here. But this term is negligible, yeah, when k is big enough. So that's why the factor is bigger than 1 minus epsilon lambda. And this is like something close to 1. All right. At least, does it make sense? Like the small direction shrink quickly, the big direction remains there, and that's why you're gonna converge to the big direction. That's the idea. Yeah. Now suppose what if we want a second largest eigenvector, like or second large. So what I mean is, suppose that we know, suppose that I know somehow the exact first eigenvector, and suppose that I know v1, which is the first eigenvector of M. Now how can I get the vector y such that this ratio of y is as big as lambda 2, where y now need to be orthogonal to the v1. Okay. Well, how to do that? It's gonna be almost the same. Well, you start with random x, but you just make x orthogonal to v1 just by remove the direction of v1 from x. And now apply the same algorithm, but now the algorithm will just work inside the space, which is orthogonal to v1. Use the same analysis. That's how you get this y. Okay. Yeah. And when you apply the same analysis, you can see that like the ux here will be, everything is the same except that you remove the first coordinate, like the coordinate that is parallel to v1, you remove it. And apply the same thing exactly, then you are done. Okay. So now we are kind of close to what we want. Now let's come back to our problem where we want a smallest, not the biggest. We want a smallest one, like second smallest one. What do we do? Like, so okay. We know this. Sorry?
Are we taking the inverse then?
Yeah, the inverse is a good, like is a good thing to try actually, but it's not super clear yet that it's gonna be fast, because if you want to do the inverse, then you need to be able to, like, when you apply, I will talk about it, yeah, but it's a very good thing to, and actually it's the fastest way to do it actually, but I would talk about easier one first. Yeah. So we know how to get a second largest one. Now we want a second smallest one. Well, what do? We will just kind of flip thing. Not the inverse, but we have that our eigenvalue of second, like of normalized Laplacian is between 0 and 2. So if I consider M to be just 2i minus this matrix, which is can be written like this, but doesn't matter. Then we will have that the eigenvalue of M is going to be in this way, right? The biggest is 2, then and then keep decreasing. So now, but we kind of know how to get the second largest eigen value from M. But if we get the approximation of this, we should get the approximation of lambda 2, which is the second smallest eigen value of n. All right. Okay. So so now, and note that to get the second smallest eigenvalue here, like to apply the to do that, we need like the first eigenvector, right? So that we can work on the space that orthogonal to that. But we know that explicitly without needing to do anything, at least for Laplacian. We know that, like by analysis. We don't need to compute it. So that is just like the eigenvector V1, which corresponds to the largest eigenvalue here of M, is just the same thing as the one for Laplacian, which we showed before that is just this vector. So you can just run the power 2 algorithm, start by some random x, make it orthogonal to V1, and apply the algorithm. And then you get the vector y such that it's orthogonal to V1. And this ratio is going to be at least what? So this ratio is going to be at least this thing times the second largest eigenvalue of M, which is this thing, right? And I multiply this to this, then like it's gonna be something like this within some constant factor. All right, so we get this thing. And now, now do some math from here. Like M is simply 2i minus Laplacian normalized Laplacian. You rearrange things, then you get that y, this quotient, relay quotient of y for normalized Laplacian is going to be at most this. And how much time does it take? Well, recall that you will set k to be something like this. So, and the non-zero of ng is just the number of edges in the graph. So the total time is m over epsilon, right? So it means that now we can just get the vector y that we want from Shiger-Cut algorithm, and it's called feeder algorithm actually. Yeah. We get this vector y, which is almost as good as a second eigenvector, and we apply this, and we get a cut. We apply the algorithm, and we get a sparse cut with this additional time. So very fast, right? You first get this vector in m over epsilon time and spend linear more time to be done. Now there is a very important caveat. That is, note that here is an additive approximation. Lambda 2 can be as small as n over 1 over n squared. So this additive approximation, like if you want multiplicative approximation, you need to set epsilon to be as small as this. And that is bad, right? It's not gonna be linear time anymore. So that is when you write if you want 1 plus epsilon prime approximation, multiplicative approximation, the epsilon that you need to put here is like epsilon prime lambda 2. And the total running time is here, which can be as bad as here because of Shiger inequality. So, okay, it's fast when the graph is an expander, but it's very slow still. And the way to make it fast actually is to work with inverse that you suggest. But there is some non-trivial step to make that idea work. But before that, at least it's fast when phi is big. Okay, and there is one of my favorite open problem here. That is, suppose that phi is actually big. Suppose that you know that phi is either zero, constant, or phi is 1 over log to the 100. Can we decide which case it is? Like if it is a very good expander or have some sparse cut? Can we do that can we decide which case it is in nonlinear time, but do it deterministically? So you can see that what we just learned completely solve this easily in nonlinear time, but randomized. What is step which is randomized?
Picking the y vector, x vector.
Yeah, use a random x from the power method. That's the only randomized step. Everything else is completely deterministic. And it's very simple, and it solves this thing completely in linear time. Can you do it deterministically? That's a big open problem. We can do it close to linear, but it's slower by a polynomial factor. But if you can do it in nonlinear time, it's very likely that it can be used to speed up a lot of other things, and you will get a really good thesis from here. Yeah. Okay. So I have a lot of intuition to tell you on this thing, but I think I should stop for today. So basically, in the exercise session, so you see that the algorithm is super simple, but actually we can interpret the algorithm as some diffusion process, like some averaging process between nodes. So it's very nice to see the intuition and the video. So I will show this in the exercise session tomorrow. And you will see some nice picture here too. And some video. Yeah, but that's tomorrow. Okay.
6:30. So should I go and inform?
Do you have that? Sorry.
So regarding the meeting, I asked you like I'm working on the assignment. And I couldn't.
Yeah. So we can just meet next week or something.
I should inform the second.
You can. Yeah. Sure. Yeah.
Actually, I was thinking to make, but I didn't make it actually.
I see.
Yeah.
He wouldn't mind. So. Yeah.
Oh, okay.
Yeah.
I'll just go ahead and inform you.
Sure.
Thank you.
Yeah.